Hi everybody, this is a lecture on section 6.1, products, lengths, and orthogonality. So, definition, given vectors u and v in Rn, define the dot product or inner product so it's called either or, dot product or inner product, as, so you write u dot v, and that's just simply equal to u transpose times v. So for example, in R3, if I have a couple vectors here, 1, minus 1, 3, dot 2, 1, 1, this is equal to, you take the transpose of that, and take the ordinary matrix product, like this, right? This is the ordinary matrix product here, and that we denote it as the dot product, but this transpose is just the corresponding row vector, like that. And this is 1 times 2, plus minus 1 times 1, plus 3 times 1. So that's 5 minus 1 is 4. And you'll notice that it's a real number, right? The dot product is a real number. Now, some properties of the dot product. Okay, one, u dot v is equal to v dot u. It's commutative. It distributes over vector addition. So this is the sum of u and v, and this is some vector w. So if you take the sum of u and v, the dot product with w, this is u dot w plus v dot w. So this is a real number and that's a real number. So this is addition within the real numbers. This is addition within vectors. Right? So it's a distribution property, but it's a little deeper than it might at first appear. If you have a scalar k times u dot v, that's the same as the scalar k times u dot v. Unsurprisingly, for u dot the 0 vector is the 0 real number, right? Certainly that's true. All right, I mean, we could do like a quick example up here. 1 minus 3, 1 dot 0, 0, 0, right, is 1 times 0 plus minus 3 times 0 plus 1 times 0, and that's just 0, right? So vector dot 0 vector is 0 scalar, right? And 5 u dot u is bigger than or equal to 0 with u dot u equal to 0 if and only if u itself is the 0 vector. Okay? And it's bigger than or equal to 0 because you're taking the product of u with itself. So every term in the sum is a square, right? So I mean, let's look at say number 2, right? Number 2 is, so I mean, if you have this vector u plus this vector v dot product this vector w, like that, that's equal to, well, it's the vector a1 plus b1, a2 plus b2 dot c1, c2, which is equal to the sum a1 plus b1 times c1 plus a2 plus b2 times c2, so on and so forth like that. So we're proving number 2. Right, but real numbers, these are real numbers, and we know that distribution works over the real numbers. B2, C2. And we know that addition is commutative. B1, C1 plus B2, C2. Like that. But this is just A1, A2 dot C1, C2. And this is just B1, B2 dot C1, C2. Right? So that's what we wanted to prove. All right, u plus v dot w is equal to u dot w plus v dot w. Right? So it's just a straightforward calculation. And then number 5, if you just take a vector dot itself, dot a1, a2, right, what do you get? You get a bunch of squares, which is bigger than or equal to 0, with equality if and only if a1 equals a2 equals 0. And only if they're all 0, right? Because a bunch of squares, it's always positive. It's always 0, only when it's actually equal to 0. Any one individual square, so any sum of squares satisfies the same thing. All right. So basics on the dot product there. The length, or norm, it's often called, of a vector v is denoted as just like the absolute value of v, which is the square root of v dot v, right, which is equal to a1 squared plus a2 squared plus an squared when v is equal to, well, so maybe we'll do it here, whoops, of a vector v equal to a1, a2, an, like that, is like that. Now why is it called the length? Because in like 2 and 3 dimensions, I'll just explain it in 2 dimensions, it actually is the geometric length. So if v is equal to ab in R2, then, right, I mean, we look at this vector here, right, if this length here is a, and this length here is b, right, then that vector right there is AB, but this length here is A, and this length here is B. So by the Pythagorean theorem, this length right here is the square root of A squared plus B squared, right? Which is the square root of V dot V, right? V dot V, sorry, length of V and geometrically it is the actual length of the line segment from point 0, to point AB, right? So that's why it's called the length. Although it's often called the norm. And why is it called the norm? Well, it's unfortunate that they're presenting the material in this way. It's called the norm because, I mean, this is all about the dot product. This product is always called the dot product, really. But it's also, they say inner product. And what do they mean by that? Because this generalizes significantly to lots of different vector spaces in lots of different ways. And even in Rn, it has lots of different forms that are really quite similar to this. In particular, you can define something like this: UV is equal to UAV for some invertible A. And it's got enough properties that all of the stuff that we're talking about carries over into this new type of product. I mean, there's even ways of doing it with polynomials and integrals. And anyway, things no longer represent length. Or it's not a dot product anymore. So they have more general names like norm and inner product. So you can use either word that you want. Length, norm, inner product, dot product. It's all the same. So here it actually represents length geometrically. Some properties. Oh, one other thing before we move on. In that definition. So a vector V is called a unit vector when the length of U is 1. Okay, so length 1 is called a unit vector. Some properties. One, if you have the length of a scalar k times vector V, that's the absolute value of k times the length of V. 2, well, just because it's defined that way, the length of V squared is just V dot V. That's just the definition of it. And 3, if the length of V is not 0, then the scalar 1 over the length of V times V is a unit vector. So, for example, so let's say V is equal to, is a unit vector which points in the same direction as V. So, for example, if V is equal to 3 minus 1, 1, then the length of V is square root of 9 plus 1 plus 1, which is 11. So 1 over the length of v times v is 1 over root 11 times v is 3 over root 11 minus 1 over root 11, 1 over root 11, like that, is a unit vector in the same direction. As v. So in other words, if v looks like this, then 1 over v times v, I mean, if v has length less than 1, or bigger than 1, then it gets shorter. If it has length less than 1, it gets stretched a little bit. So there's v, there's, the unit vector 1 over v times v. Okay. Definition: the distance between u and v is defined as the norm of u minus v. In 2 dimensions, in R2, u minus v is the length of the head-to-head diagonal of the parallelogram defined by u and v. So u plus v is one diagonal of that parallelogram. That's the tail, head. And so this is u, we'll call that v. Right, the tail, head diagonal, the parallelogram, is u plus v. Oops. Right, so this diagonal here, tail, head, that's u plus v. But this diagonal here, I mean, depending in which direction you draw it, right, either going right to left or left to right, this is v minus u, the way I've drawn it. It's u minus v in the other direction, right, because u plus v minus u is v. Right, so, and when you add vectors head to tail like this, that's when you get their sum, right? U plus v is u plus v. So u plus v minus u is v. So anyway, it's just the length of that other diagonal of this parallelogram. Okay. So given that notion, this is a nice outcome here. So in R2, if you have 2 vectors u and v, you've got this angle theta between them. Right, so there's always two angles. I mean, there's theta and then there's alpha, where alpha plus theta is 360. Look at this angle alpha, which is less than or equal to pi radians, equals 180 degrees, right? So there's always one that's less than 180 degrees, less than or equal to. All right, well, this looks more magical than what it is. Cosine theta, the cosine of that angle, is u dot v over the length of u times the length of v. So, I mean, it looks way complicated, but it's actually just the law of cosines in there. Proof. So in this picture here, using the law of cosines from your pre-calculus trigonometry course, the length of u minus v, or v minus u, same thing, the length of u minus v squared is equal to, well, it's the length of u squared plus the length of v squared. Let me draw that picture over again. All right, here's u, here's v, and then here's u minus v, and here's the theta. So using the law of cosines, right, this is the Pythagorean theorem when this theta is 90. When the theta is not 90, right, you've got the law of cosines. U minus v squared is u squared plus v squared, right, minus 2 length u length v cosine theta when theta is not 90 degrees. When theta is 90 degrees, cosine of theta is 0. Okay? The length squared is just the vector dot itself. I'll leave it like that. Length of u squared plus length of v squared minus 2 length u length v cosine theta. Well, this is, using distribution, u dot u minus v dot u minus u dot v plus v dot v. Right, but u dot u is the length of u squared. And then u dot v is the same as v dot u, right? It's commutative, so this is minus 2 u dot v plus the length of v squared. Cancel, 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 cancel. So minus 2 u dot v is equal to minus 2 length u length v cosine theta. Now cancel, cancel, and divide. U dot v over length u length v is equal to cosine theta. And that's what we wanted. So what does that say about orthogonality? So as a consequence, okay, u and v in R2 are perpendicular, right, or orthogonal. That's another word for it. When their angle is 90 degrees. But when their angle is 90 degrees. But this angle, theta, is 90 degrees if and only if length u dot v over length u length v is equal to cosine of 90. If and only if u dot v over, well, I'll put the length u length v over here. Length u length v is times 0. Right, but that's just 0. If and only if u dot v equals 0. Well, no, I can move it underneath that. Doesn't need to be like that. U dot v over length u length v is 0. If and only if, well, as long as these vectors are not 0 themselves, in which case it's orthogonal anyway, a fraction is equal to 0 if and only if the numerator is equal to 0, right? 0 over 9 is 0. You can't divide by 0. 9 over 0 is undefined. Right? A fraction is equal to 0 when the top is 0. So perpendicularity is just given by the dot product. So for example, like 3, 4 dot minus 4, 3, right, is equal to minus 12 plus 12 is 0. So those guys are perpendicular. In R2. But we extend this notion into any Rn. For any n, we say that u and v in Rn are orthogonal when u dot v is equal to 0. We say the angle between u and v satisfies cosine theta is equal to u dot v. I mean, you know, as far as we're concerned, this notion really kind of only makes sense in 2 dimensions. I mean, what do you mean by the angle between 2 vectors in higher dimensions? Well, you know, 2 vectors create a plane, and in that plane you have this angle, and yeah, the angle is going to be that. But we don't need to get that deep into it for this course. But the cosine of the angle in the plane created by those 2 vectors is indeed that. Okay, so, and then that angle is 90 degrees if and only if u and v are perpendicular in that plane, if and only if cosine theta is 90 degrees. So there it is. So let's do a little problem here. Find a unit vector such that u and 1, 2 form a basis for Rn. Well, no, I'm sorry. Find a unit vector u that is orthogonal to and forms a basis R2 with 1, 2? Well, once they're orthogonal, they have to form a basis because it'll be two linearly independent vectors. Vectors that are orthogonal, they can't not be linearly independent because they just don't point in the same direction. They have to be linearly independent. So anyway, so let U equal A, B. All right, so since it's a unit vector, A squared plus B squared, right, the length of U is 1, so the length of U squared is 1, so A squared plus B squared is 1. Also, 1, 2 dot AB is equal to 0, so A plus 2B is 0. So from here, A squared, well, okay, so let's combine these. So A is equal to minus 2B, so A squared plus B squared equals 1 becomes 4B squared plus B squared is 1, so B squared is 1/5. So B is plus or minus 1 over root 5. Let's pick B equal to 1 over root 5. So then B is 1 over root 5. So A is minus 2B is minus 2 over root 5. So 1, 2, and minus 2 over root 5, 1 over root 5 is a basis of orthogonal vectors in R2 with the second a unit vector. Now in R2, orthogonality is actually like not quite so mysterious. In R2, if U is equal to AB, then V is orthogonal to U if and only if V is equal to minus KB, KA for some K. That's just in R2, right? That's the whole thing about negative reciprocals with perpendicular lines and all that in R2. But in R3, it's more complicated than that. But it's just some, just some ideas of how you might solve such a problem, in dimensions higher than 2 are given in this solution rather than just trying to use this solution in R2. Final idea, topic here. Section 6.1 is the following. Orthogonal complements. If W is a subspace of V, then W perp, it's called, is the set of all vectors W which are perpendicular to, or I guess we'll say V, which are perpendicular to every vector of W. So it's the vector space of all vectors that are orthogonal to vectors in W. So you write it like this. W perp is equal to the set of all V such that V dot W is 0 for all W in W. and we call, so sometimes we say W perp, but it's really called the orthogonal complement of W, or it's called the dual space in some of W. So orthogonal complement or dual space. So basic facts here. W perp is a subspace of V. And for an example, not fact, but fact, this is a great example. Given an m by n R by C matrix A, given an R by C matrix A, the row space and null space of A are in what? They're in the number of columns, or subspaces of RC. And, well, the row space of A, the orthogonal complement of that is the null space of A. Why? Right, the null space of A is equal to the set of all vectors V such that A times V is equal to 0. And the row space of A is the span of the row vectors. Right, so if you have a column vector, so here's A, and here's V, like that, and you're and it's supposed to be equal to 0, like that, then every row in A times the column vector V should be equal to 0. So this row dot product that column, row dot column, right, row dot column needs to be equal to 0 for every row. Right, so because R U V is equal to 0 for every row U in A. So since the rows of U in A form a basis for the row space of A, well, you're going to be orthogonal to every vector in the row space of A because you're orthogonal to every basis vector. So that's a really nice result. And similar to this is the following. The column space of A transpose, the column space of A transpose is just the row space. The column space of A perp is equal to the null space of A transpose. So just in a very similar fashion. So the orthogonal complement of the column space of A is the null space of A transpose, where both column space of A and the null space of A transpose are subspaces of R to the R. Okay? So that's the lecture on section 6.1.